Hello guys! So we start the second module with a discussion on the basic concepts in chemical equilibrium. In this lecture, you'll be able to define the different concepts related to chemical equilibrium. Also, you will be able to determine the chemical equilibrium constant expression for a given reaction. Then, you will be able to predict the shift of equilibrium based on Le Chatelier's principle. And finally, you'll also be able to calculate the equilibrium concentrations using the icebox method. In your past chemistry courses, you became familiar with unidirectional reactions wherein the reactants get consumed to form products. And once the limiting reactant is completely depleted, the reaction just stops. Through stoichiometric calculations, we can determine the amounts of products formed based on the amounts of reactants consumed, or vice versa. However, there are reactions that are considered reversible. This means that the forward and backward reactions are happening simultaneously. Given in the example here is the reversible conversion of nitrogen tetroxide N2O4 to nitrogen dioxide. The forward reaction is the conversion of N2O4 to NO2, while the reverse or backward reaction is the conversion of NO2 to N2O4. This makes the stoichiometric calculations a bit more complex than the unidirectional reaction because as the reactants get consumed to form the products are also converted to form the reactants. So in the succeeding slides, you will see that a different approach will be done to determine concentrations in a reversible reaction. Over time, reversible reactions also attain a state of chemical equilibrium wherein the rate of the forward and reverse reactions are equal. When you observe a reaction in equilibrium, it would seem that there is no activity because the reactants are formed at the same rate as the products. There are two characteristics of chemical equilibrium. The first one, as I have mentioned in the previous slide, is that the rates of the forward and reverse reactions are the same. If you look at the rate versus time graph of the reaction of N2O4 and NO2, the reaction progresses towards the attainment of equilibrium or equal rates. It is well noting that the tendency of reversible reactions is to always attain equilibrium. Another characteristic is that concentrations become constant. This concentration is called the equilibrium concentration. Like mentioned, at equilibrium, products and reactants are produced and consumed at the same rate. This results to having no more change in their concentration. In this concentration versus time graph, you will see that at the initial part of the reaction, N2O4 gets consumed, lowering its concentration, while NO2 is produced. However, as the concentration of NO2 increases, the rate of the reverse reaction also increases, which then produces N2O4. This increase in rate is also shown in the rate versus time graph. That's why, in a reversible reaction at equilibrium, no compound is really completely depleted. Now, what if we change the concentration of the reactants? Will equilibrium still happen? Or what if we start the reaction by doing the reverse reaction first? Will the forward reaction happen and will equilibrium be reached? The answer for these questions is yes. Equilibrium can be reached from either direction of the reaction as long as temperature is held constant. Take this experiment for example. If you look at these three datasets, you will see that it was done at varying concentrations of NO2 as initial reactant. The equilibrium constant, which is used to describe the reaction in equilibrium, is generally the same whatever initial concentration is used. We will talk about the equilibrium constant more in the succeeding slides. This means that whatever initial concentration is used, the same equilibrium will be achieved. Now, looking at the last two sets of data, you will see that regardless of whether you start with NO2 or N2O4 as the initial reactant, the same equilibrium constant is achieved. Again, equilibrium will be reached from either direction of the reaction. Same with this example, whether the reaction is started with nitrogen and hydrogen or with ammonia, the same concentration proportions for each substance will be achieved at equilibrium. Now let's talk about the equilibrium constant. It is represented by Kc or Keq or simply K. It is the relationship between the reactants and products at equilibrium for a specific temperature. Let's consider this general equation wherein reactants A and B form products C and D. Note that the small letters A, B, C, and B are the coefficients of the balanced reaction. The equilibrium constant is obtained by multiplying the molar concentration of the products, each raised to their stoichiometric coefficients, divided by the product of the molar concentrations of the reactants, each raised to their respective coefficients. As you can see, in writing equilibrium constant expressions, it is very important that you have the correctly balanced chemical equation. Take note also that only gases and aqueous substances are considered in the equilibrium constant. Therefore, solids and pure liquids do not appear in the expression because their concentrations rarely change and they don't affect the position of equilibrium. Now, why do we need to determine the equilibrium constant? The value of K tells us whether the reactants or products are more favored in equilibrium. If K is greater than 1, the numerator is larger than the denominator, therefore, more products are present at equilibrium or the reaction is product favored. On the other hand, when K is less than 1, the denominator is larger than the numerator, which means that more reactants are present at equilibrium or the reaction is reactant favored. Now let us practice writing equilibrium constant expressions from reactions and vice versa. If you want to solve the problem first on your own, you may pause this video. For the first reaction, just remember the general formula for equilibrium constant. The numerator shows that the products raised to the power of their coefficient. For this case, that is oxygen or O2 raised to 3, and the denominator presents the reactants raised to their coefficient or ozone O3 squared. For number 2, you will see that if given the equilibrium constant expression, you can also determine the reaction. But you have to be careful because there are substances that do not appear in the K expression, such as solids and pure liquids. Knowledge on different reactions will help you identify if there are such substances in the reaction. However, for this problem, it is specified that all substances are in gaseous form, thus they all appear in the expression. To get the balanced reaction, remember that reactants are written in the denominator and exponents represent coefficients. Therefore, the reactant side is 2NO plus Cl2. And then the product side is 2NOCl, which is seen in the numerator of the K expression. Finally, for the last reaction, as mentioned, remember that solids are not included in the equilibrium constant expression. Therefore, the equation will just be copper 2 plus divided by Ag plus squared. Now we move on to operations involved in writing equilibrium constants. But before we do that, let us define some variables. We let Kc as the equilibrium constant of the original reaction, while K'C will be the equilibrium constant of the new reaction. So first rule in writing equilibrium constant expressions, if a chemical reaction is reversed, or the forward and backward reactions are exchanged, K'C is just the reciprocal of Kc. For example, consider the conversion of N2O4 to NO2. Its equilibrium constant expression is equal to the square of the molar concentration of NO2 divided by the molar concentration of N2O4. Now, if we reverse this equation, we'll get this one. NO2 yields N2O4. K prime C will now be equal to the molar concentration of N2O4, which is now our product, divided by the square of NO2, which is now our reactant. Simplifying, this is just the reciprocal of the original equilibrium constant expression. Second, if a reaction is multiplied by a certain factor, the new equilibrium constant is equal to the original equilibrium constant raised to a power equal to the multiplied factor. For example, if we multiply the given equation by 2, as shown in this equation, the new equilibrium expression will then be NO2 raised to 4 divided by N2O4 squared. When we simplify this is just equal to the square of the original equilibrium constant expression. Third, when a reaction is divided by a certain factor, K prime C will just be equal to the corresponding root of Kc. For example, dividing this reaction by 4 or simply multiplying it by 1/4 means that you have to raise the original expression by 1/4, which is also equivalent to the fourth root of that expression. Finally, the equilibrium constant for a net reaction that is made up of 2 or more steps is equal to the product of the equilibrium constants of the individual steps. For this operation, you also have to remember the rules for getting the net reaction. For example, in the first reaction, substances A and B react to form substances C and D. This reaction has a corresponding equilibrium constant, or Kc1. In the second reaction, C and D reacts to form substances E and F. This reaction also has a corresponding equilibrium constant, which is Kc2. Their net reaction is obtained by adding the two equations. Note that substances that appear on both sides of the equation are cancelled. This gives us a net reaction of A plus B yielding E and F. The equilibrium constant of this reaction is obtained by getting the product of Kc1 and Kc2. To further explain the operations discussed, let us consider this guided problem. Determine the equilibrium constant of the reaction N2O plus 1/2 O2 yielding 2NO. You are given two equations with known equilibrium constants as shown. If you wish to solve the problem first on your own, you may pause this video. To determine the net equilibrium constant, you have to modify the given reaction such that, when added, will give the net reaction. First, let's look at the reactants of the net reaction. We need to have N2O and O2. N2O can be obtained when we reverse the first reaction. Remember, when you reverse a reaction, the new equilibrium constant will be its reciprocal. So for the reversed reaction 1, K prime 1 will now be equal to 3.704 times 10 to the 17. Next, the reactant O2 and product NO can already be obtained from the second reaction without the need of any modification. Adding the two chemical equations and cancelling like terms, we get the net reaction N2O plus 1/2 O2 yielding 2NO. The corresponding equilibrium constant will be the product of K prime 1 and K2, which gives us 1.741 times 10 to the negative 13. When a reversible reaction is not in equilibrium, the equilibrium constant may not be applied. Therefore, we introduce another expression that is meant for such reactions, which is called the reaction quotient, or Q. If the reaction A plus B yielding C plus D is not in equilibrium, then its reaction quotient will be equal to this expression. You may see that the expression is the same as that of the equilibrium constant, except that the concentrations used here are not equilibrium concentrations. Now, what does the reaction quotient tells us? Like I have said earlier, the tendency of reversible reactions is to always attain equilibrium. Comparing the values of Q and Kc will tell you which reaction will be favored to reach equilibrium. If Q is less than K, that means the forward reaction is favored because more product must be formed to attain equilibrium. Likewise, if Q is equal to 0, then its value is less than K, which again favors the forward reaction. If Q is very high and is greater than K, then the backward or reverse reaction is preferred because more reactants must be produced to achieve equilibrium. When Q is equal to K, then it means that equilibrium has been reached. Now, what could happen that would cause a reaction to deviate from equilibrium? This deviation can be caused by a stress or something that changes the condition of a system in equilibrium. This could be in the form of changes in concentration of the reaction species, temperature, pressure or volume, or the addition of a catalyst. But since reversible reactions always tend to proceed towards equilibrium, a change in condition will cause the system to readjust so that equilibrium can be restored. This principle was introduced by the chemist Henri Le Chatelier. Le Chatelier's principle states that when a system in equilibrium is subjected to a change in temperature, pressure, or concentration of a reacting species, the system responds by attaining a new equilibrium that partially offsets the impact of the change. Simply put, it means that when stress is applied on the system at equilibrium, the system will shift so as to relieve that stress. So let's study the different stresses that could be applied in a system at equilibrium. First, we have concentration. Equilibrium can be disturbed by the addition or removal of reacting species in the system. Say we have a chemical reaction in equilibrium such that there is balance between the reactants and products. When reactants are added or products are removed, the system will become unbalanced such that more reactants are now in the system. This will cause the system to shift to the right or the forward reaction to make more products and thus restoring equilibrium. Similarly, when reactants are removed or products are added, the system will now have more products which will then shift the reaction to the left or the reverse reaction which will make more reactants and achieve equilibrium. Next, what happens to a system when the temperature is changed? The shift in reaction depends on whether the reaction is exothermic or endothermic. Recall from your Eng201 course, exothermic reactions are those that release energy in the form of heat, such that we can write energy as one of the products in the reaction. On the other hand, endothermic reactions are those that absorbs heat. We can then treat energy as one of the reactants since heat is needed for the reaction to proceed. If we write the reactions this way, we can treat energy as just another substance in the equation. Increasing the temperature will shift the reaction towards the opposite side so as to release some excess heat and restore equilibrium. Decreasing the temperature will have the opposite reaction. When there are gaseous substances present in the system, changes in pressure and reaction volume can cause some shifts in equilibrium. Recall that pressure is characterized by the collision of gas particles on the walls of the reaction vessel. Increasing the pressure means more collisions are happening in the system, so the reaction will shift in favor of the production of fewer particles so that collisions will decrease, and thus alleviating the pressure. Decreasing the volume will also have the same effect because based on Boyle's law, a decrease in volume will cause an increase in pressure. Let's consider this decomposition of nitrosyl chloride or NOCl to nitric oxide NO and chlorine gas. The reactant side has 2 moles of gas particles while the product side has 3. Increasing the pressure or decreasing the volume will shift the reaction to the left to produce less particles by combining NO and Cl2. In contrast, decreasing the pressure or increasing the volume will shift the reaction to the right to create more particles to increase the pressure towards equilibrium. Let's consider this next reaction. Water vapor reacts with carbon monoxide to produce hydrogen and carbon dioxide gases. For this case, you will see that the reactant and product sides both have 2 moles of gas particles. Therefore, even if pressure and volume are changed in the system, the equilibrium will not shift because both forward and reverse reactions produce the same number of particles. So we can say that for reactions with equal number of particles on both sides of the reaction, pressure has no effect on equilibrium. Finally, let's see what is the effect of adding a catalyst into a system at equilibrium. A catalyst is a substance that enables a chemical reaction to proceed at a faster rate due to the lowering of the activation energy of the reaction. Since a catalyst increases the rate of both the forward and reverse reactions at the same extent, there will be no difference in the equilibrium position. The only change is that equilibrium will be attained at a shorter time. Now let's check your comprehension of Le Chatelier's principle. Determine which direction will the equilibrium of the given reaction shift to if the specified stress is applied. If you want to answer the problems first on your own, you may pause this video. First, what would happen to the given reaction if the volume of the reaction vessel is decreased? Remember, decreasing the volume causes the pressure to increase. So, the system will shift towards the production of lesser particles. Therefore, equilibrium will shift to the right because the product side only has 2 moles versus the reactant side with 4. Next, for the given endothermic reaction, what would happen if the temperature is decreased? Again, endothermic reactions are those that absorbs heat or has energy in the reactant side. Thus, decreasing the temperature will shift the equilibrium to the left or the reactant side. Third, what happens if an inert gas is added to a system held at constant volume? When a system has constant volume, the molar concentration of the reacting substances will not change because the number of moles and total volume are still the same. Recall, molar concentration is equal to the moles of solute or the substance divided by the total volume. Therefore, there will be no change in equilibrium. But what if the inert gas was added at constant pressure instead? More gas particles will then cause the volume to increase, which will shift the equilibrium to the right to produce more reacting particles. Now let's discuss how to determine concentrations for a reversible reaction. Like I have said at the start, calculating the amounts of substances in reversible reactions is different than what we have been doing so far for unidirectional reactions. For reversible reactions, we use what we call the icebox method to determine the concentrations of substances. This stands for initial amount or concentration, change in amount or concentration, and equilibrium amount or concentration. To illustrate how this is done, let us consider the reaction of hydrogen and iodine to produce hydrogen iodide gas or HI. To construct the icebox, each column represents the substances in your reaction, while the rows indicate the initial, change, and equilibrium amounts. Let us assume that we start the reaction with 1 molar each of hydrogen and iodine gases. So you write 1 for each reactant, while 0 for HI because it was not in the system at first. For the change, you have to indicate how much of the reactants were consumed and how much product was formed during the reaction going to equilibrium. Let's say X molar was consumed from hydrogen gas. Looking at the stoichiometric relationships, we know that for every 1 mole of hydrogen consumed, 1 mole iodine is also reacted and 2 moles of HI are produced. Take note that a negative sign for reactants are indicated because they are being depleted, while a positive sign for the products are placed because they are being formed. The equilibrium concentration is determined by getting the sum of the values for the initial and change rows. Therefore, we have 1 minus x for both hydrogen and iodine, while 2x for HI. Take note that we could also express the values in terms of moles instead of molarity, as long as the total volume is constant. To understand better, let us consider this problem. 1 mole hydrogen gas and 1 mole iodine vapor are introduced into a 5-liter sealed flask. The mixture is heated to a certain temperature and the following reaction occurs until equilibrium is established. At equilibrium, the mixture is found to contain 1.58 moles of HI. What are the concentrations of hydrogen, iodine, and HI at equilibrium? And then calculate the equilibrium constant Kc. If you wish to solve this problem first on your own, you may pause this video. First, we put the given values in our icebox. For this problem, we will use moles instead of molarity. The initial amounts of hydrogen and iodine are 1 mole each, while no HI was in the system at the start. It was also given that 1.58 moles HI was found at equilibrium. Since we know that the initial amount of HI is 0, the change for HI is just also equal to 1.58 moles. By stoichiometry, we can get the change in hydrogen and iodine by dividing 1.58 by 2. Again, do not forget to put in the negative sign for reactants to indicate that they are being consumed. To get the equilibrium amounts, simply add the initial and change rows. We get 0.21 for both hydrogen and iodine gas. To determine the concentrations, we just simply divide the equilibrium moles by the container volume of 5 liters. We get 0.042 molar for hydrogen and iodine and 0.316 molar for HI. To calculate the equilibrium constant, first, write the correct equilibrium expression. Remember that the equilibrium constants are calculated from equilibrium concentrations in molarity and not moles. Thus, it is important to obtain the molar concentrations first before being able to calculate Kc. Substituting the molar concentrations in the equation, we get Kc is equal to 56.608. Let's try another example. A 0.5 mole HI is introduced into a 1-liter sealed flask and heated to a certain temperature. Under this condition, HI decomposes to produce hydrogen and iodine until an equilibrium is established. Calculate the equilibrium concentrations of hydrogen, iodine, and HI if the equilibrium constant for the following reaction is 0.0177. As you may have noticed, the given reaction is just the reverse of the reaction from the previous problem. You may also check that the equilibrium constant of this reaction is just the reciprocal of 56.608, which we have obtained earlier. So again, to analyze this problem, we will construct the icebox. For this case, we will now use molarity as our unit just to show that it will also work the same way as the previous problem wherein we use moles. It was given that initially there was only 0.5 moles HI in the system. Dividing this by the container volume of 1 liter, we get the initial concentration of HI as 0.5 molar. Hydrogen and iodine both has 0 initially because they are not present at the start. It was also given that the equilibrium constant is 0.0177 and it's equal to this expression. Since we still don't know the amount consumed or produced, let's set X as the concentration of hydrogen and iodine produced in the reaction. Therefore, 2X was consumed for HI. Again, do not forget the negative sign. To get the equilibrium concentration, add the initial and change rows. So we get 0.5 minus 2X for HI and X for hydrogen and iodine. Then, we substitute the equilibrium concentrations to the equilibrium constant expression. This will give us an equation with one unknown. Therefore, we can solve for X, which is equal to 0.0525 molar. Now that we know the value of X, we can solve for each of the equilibrium concentrations, which would give us HI is equal to 0.395 molar and hydrogen and iodine are equal to 0.0525 molar. So this ends lecture 4A. Thank you for listening and see you in our synchronous session.